We're starting the first part of Unit 7, which is about solutions, and that is when something is dissolved in something else. We have qualitative ways of talking about this, that some of them are common that we use every day, but then chemists have some quantitative ways of describing solutions and working with solutions, as this is a common way to see reactions happen in chemistry. Today we're going to be looking at a few qualitative ways and one quantitative way to describe how concentrated solutions are. First, some basics, some terminology. One term that we use in describing solutions a lot is solvent. Solvent is the medium into which the solutes are dissolved. This is typically the largest part of the solution. For example, in Kool-Aid, if you're making Kool-Aid, which is a solution, water is the solvent. That's what you dissolve the other stuff in. You dissolve sugar in there, you dissolve all the little stuff from the packet, but the solvent, the largest part of the solution, is water. Another term that we use is solute. Solute is any substance that's dissolved in the solvent. Some solutions have only one solute, some solutions have lots of solutes. Kool-Aid is a good example. Kool-Aid has sugar in it, and that stuff in the packet, if you read the ingredients, there's more than a half a dozen substances in there. They all are solutes when Kool-Aid is made. So solvent is the big part of the solution. That's what dissolves everything. Solutes are what are dissolved in the solvent. When we talk about solutions, we often talk about concentration, and this is a way of measuring how strong the solution is in common language. Really what it comes down to is a measure of the ratio of solute to solvent. We have a couple of qualitative descriptions that we use. One is called dilute. In a dilute solution, the ratio of solute to solvent is relatively low, and that's a key term there, relatively low. Here's an example of some Kool-Aid that's been made dilute. You can tell that this red color is the color the Kool-Aid's supposed to be, the color that's the Kool-Aid man is, and this looks weaker. We can tell that it's dilute because we have a basis for comparison. Because we know it's supposed to be this darker red, we know this is dilute. So relative to what Kool-Aid is supposed to be, that's dilute. Another relative qualitative description of solution concentration is just the word concentrated. In a concentrated solution, the ratio of solute to solvent is relatively, again, high, relative to some fixed standard. Like here's the Kool-Aid man with some concentrated Kool-Aid. If you look at the color of this Kool-Aid, it's too dark. This is the normal color of this kind of Kool-Aid that's inside the Kool-Aid man, and this is much more concentrated. And again, it's relative because you have to have some standard for comparison, which is normal Kool-Aid in this case. One concept that we use to describe concentration with a little more precision is something called saturation. A saturated solution is a solution in which no additional solute can be dissolved at that temperature and pressure. Now, if you raise the temperature, typically solid solutes will dissolve better. So like you can dissolve more sugar in hot tea than you can in iced tea. And pressure can have a factor when you're dissolving gases like carbon dioxide. Obviously the high pressure inside of a bottle of soda pop dissolves more gas than when you release the pressure. You take the cap off and all these bubbles suddenly come out because the gas can't stay dissolved in there anymore. This picture is using sodium chloride as an example of describing what saturated means. In 100 milliliters of water, which is what we have in this beaker, only 36.0 grams of sodium chloride will dissolve. That's the maximum that you can put in there. So if I start out with 40 grams of sodium chloride in this pile here, and I throw that in the beaker and stir it up and stir it up and stir it up and stir it up, I will end up with a little pile of sodium chloride in the bottom. Only 36 grams will dissolve, and that saturates the solution. The additional 4 grams, you can see it laying down in the bottom. So this is a saturated solution. No more will dissolve no matter what you do, unless you change the temperature and pressure. Well, an unsaturated solution is just one that isn't saturated yet. It contains less than the saturation quantity. So this picture shows an unsaturated solution of sodium chloride. If you start out with 30 grams of sodium chloride and you throw that in a beaker, since 36 grams will dissolve, 30 grams will dissolve easily, and there's still room for 6 more grams. So this is an example of an unsaturated solution. No little pile of stuff down in the bottom because it's all dissolved. That's an unsaturated solution. A slightly weird concept is supersaturated solution. A supersaturated solution contains more than the saturation quantity of solute, more than you're supposed to be able to dissolve. You do it by a trick. Like one example of a trick would be this. When temperature goes up, the number of grams of solute that you can dissolve goes up as well for most solid substances. So here's room temperature, say 25 degrees C. I could maybe bring a solution up to 100 degrees C to near the boiling point, and the amount that I can dissolve is much higher. It goes all the way up to this point compared with this point, which would be normal at room temperature. Then if I very, very carefully cool it down and don't disturb it, I might get my concentration to be right at this point, a very high level of dissolved solute, much higher than it's supposed to be. So all this extra amount here that's represented by this distance on the graph, that's dissolved in the solution, even though it's not supposed to be. I disturb it and it'll come out of solution. This is how they make rock candy. Make a sugar solution that's supersaturated, and then the extra dissolved sugar forms crystals. Related to saturation is a concept called solubility, and this is just a number that describes saturation. Solubility of a solute is the quantity of solute that you need to make a saturated solution with a given amount of solvent. This is often described in grams of solute per 100 grams of solvent. So for the sodium chloride example that we were looking at, the solubility would be 36.0 grams of solute, NaCl, per 100 grams of water. That would be a solubility for sodium chloride. The process by which solvent and solute become a solution is called solvation, and it happens by attraction. Water molecules are molecules that have one end that's a little bit negative and one that's a little bit positive because of their shape and the kinds of bonds that are in them. So they're attracted to particles that will dissolve when they're still part of a solid, when they're still in a crystal. We're going to look at a little animation here with some ions, but it also works for molecules that happen to dissolve in water as well. So the water molecules are jiggling around, they attract these particles, and once they're kind of attached by these attractions to the particles, they vibrate around until they sort of shake the ions or the molecules loose from the crystal. Here's a picture of a sort of a generic ionic crystal, and these are negatively charged, the little red things, and the green things in here are positively charged. Now water's H end of the H2O is positive, so the pluses here and here attract that negative. And then you're going to see that as the water molecules shake around, their attractions are going to pull that negative ion out of the structure. It gets pulled out into the water, and then it gets surrounded by water molecules, completely surrounded, so that it's unlikely to snap back into the crystal because it's not attracted to the pluses anymore that are as part of the crystal. It's attracted to the water molecules it's surrounded. It makes a sort of a shield around the ion. Now look what's happening over here at the crystal. Now we have the negative O end attracting these positive ions, and they're going to do the same thing. Those water molecules are going to jiggle around until it pulls those ions out of solution. And that process is just going to continue and continue. So now we have pluses and minuses surrounded by shields so they can't get back together. And that process continues to go on and on and on until much of the crystal, or all of the crystal, is taken apart and surrounded by these water shields. Now eventually it gets crowded in there, and that's when we've reached saturation point. When there aren't enough water molecules to make effective shields anymore around these particles, some of the solute particles are going to reform a crystal. So they're going to snap out of their shields, snap back together with each other, and make crystal again. So here's our starting point. You see crystals beginning to reform over here. That's the saturation point. The other solid has continued to dissolve, but it's undissolving at the same rate that it's dissolving. So when saturation has been reached, it's not really that there's no more dissolving happening. There is. Undissolving and dissolving are now happening at the same rate. It's sort of like juggling. A juggler has the same number of balls in the air all the time, but they're not always the same balls. And that's what's going on here. They're the same number of particles that are undissolved in solution, but they're not always the same particles because it's constantly moving around. It's an example of an important idea in chemistry called dynamic equilibrium. We're going to look at one quantitative way to describe solution concentration. There are others, but this one is really useful in chemistry because it has moles in it. It's called molarity. Here's the basic idea. This is the concentration of a solution expressed in moles of solute per liter of solution. So molarity, which is abbreviated capital M, can be defined this way: number of moles of solute divided by liters of solution. So if you were making a salt solution, it would be number of moles of salt divided by liters of, not water, but liters of the entire solution with the salt already dissolved in it. You can use this as a convenient factor in dimensional analysis to solve problems like this one. It's asking what volume of a 0.250 molar, that's how we'd say that, capital M, that means 0.250 moles per liter. What volume of a 0.250 molar, that's how you'd say this, capital M, KCl solution will provide 0.025 moles of KCl. So a KCl solution has got two things in it. One is water, and that's what mostly it is, and then dissolved in it is also KCl. This particular solution has, because of the definition here, 0.250 moles of KCl per liter of solution. Not per liter of water, but per liter of solution. And the question is, how much of this, how many liters of this solution would I need to provide 0.0250 moles of KCl? Here's how you can solve this. Set it up as dimensional analysis. 0.0250 moles of KCl. What I want to find is liters of solution, and the factor that will change it for me is this. There are 0.250 moles of KCl in every 1 liter of solution. So with moles of KCl dropping out of here, I'm going to get my answer in liters. If I take 0.0250 and divide by 0.250, I get 0.100 to 3 significant figures, liters, or 100 milliliters that would be. So if I pour out 100 milliliters of this solution, I would get 0.0250 moles of KCl. How can you make solutions that have the molarity that you want? This is an important skill in labs because we often measure moles by measuring quantities of solutions. Well, there are two ways that we make these solutions primarily. One is by dissolving a solid, like salt or sugar, to make a solution that has a planned molarity. Here are the steps. The first thing you want to do is find the mass of solute that you need to provide the moles you'd have to have in 1 liter of the solution you're trying to make. Let's say I want to create 500 milliliters of a 0.250 molar solution of NaCl. I would have to find out how many grams of NaCl this represents per liter. So here's what 0.250 molar means. 0.250 moles of NaCl are in 1 liter of solution. Just a little note about significant figures. When you have a molarity, the number of significant figures in the molarity, that has to be the number of sig figs in the moles and the liters, because that definition includes really a division problem. So I can say 1.00 liters here. Now, what do I want? I want to know how many grams of NaCl will go in a liter. So I change moles into grams by using molar mass. The molar mass of sodium chloride is 58.443 grams per mole. With moles dropped out, I'm now getting grams of sodium chloride per liter. My answer is 14.6 grams would go in every liter. The next thing you do is multiply the answer that you just got by the number of liters in your volumetric flask, by the number of liters you're trying to make. So remember, we're trying to make 500 milliliters here. Well, in liters, that's 0.500 liters. You divide by 1,000. So I'm going to take what I got, 14.6 grams of NaCl per liter, and I'm going to multiply that by 0.500 liters. Well, you can see what's happening here. I'm just making a half a liter, so I would need half as many grams. Liters cancel out. I'm going to get grams of NaCl, and half of 14.6 is 7.30 to 3 sig figs. So that's how much I'd have to weigh out. Next step, actually weigh out the solute and put it in the flask. So I go to my balance, I weigh out 7.30 grams of sodium chloride, and then I dump that sodium chloride in my 500 milliliter flask. Last thing I do, fill the flask up to the mark, and I swirl it in between to make sure that the stuff all dissolves. So I got my salt in the bottom, I pour water in here, and this line represents 500 milliliters of solution. So I'm going to swirl this around till the salt all dissolves, and then I'm going to add water until I get right up to that line, and I know I have 500 milliliters of solution, and I know I put the right amount of salt in there, so my concentration will be correct. Another way that these solutions get created, and this often is true for acids, is by diluting a more concentrated solution to a planned molarity. So you have something that's strong, like 16 moles per liter, for example, and you want to make a less concentrated solution, like 3 moles per liter. You can dilute it by just adding water, but you have to think about it a little bit because this is quantitative. So here are the steps. The first thing you can do is use the fact that molarity times volume in liters is equal to moles, and set the moles equal to each other, because all the solute that ends up in your dilute solution originally came from the concentrated solution. So you have this formula. It's sort of a shortcut for calculations. It's called the dilution solution by some people. Here's what the terms stand for. Molarity of concentrated times volume of concentrated solution is equal to the molarity of the dilute times the volume of the dilute. So you can use that to figure out how much of the concentrated solution you need. For example, say we wanted to make 500 milliliters of a 3 molar solution of HCl starting from a 12 molar solution of HCl. Well, the dilution solution here says molarity of concentrated times volume of concentrated is molarity of dilute times volume of dilute. What I want to know is what's the volume of concentrated solution that I need here, so I'll solve for it. Volume of concentrated is molarity of dilute times volume of dilute divided by the molarity of the concentrated solution. I'll plug the numbers in here now. The dilute solution's molarity is supposed to end up being 3.00 molar. The volume of dilute that I'm trying to make is 500 milliliters. The molarity of the concentrated solution is 12.0 molar. Look at what happens to units. Molarity drops out, and I'll have units of volume, which is what I want, milliliters. 500 times 3 divided by 12 to 3 significant figures is going to give you 125 milliliters. That's how much of the concentrated solution I need to dilute up to 500 milliliters to get the concentration that I want. So the next thing you do is measure out that quantity of the concentrated solution and put it in the volumetric flask. Now here's an important note. If you're diluting an acid, a strong acid, especially like this 12 molar HCl, you never want to put acid in and then dump water on it. Here's why. Because the acid is more dense than the water. The water is going to float on the surface. And before these things actually mix, there's going to be a sort of a violent reaction. And that reaction will happen on the surface, and it'll splash up out of there, screw up your concentration, and maybe even hurt you if your goggles are not on. And so you always want to pour a little water in the flask. So my first step that I'm showing here is I'm dumping a little bit of distilled water in the bottom. Then I'm measuring out my HCl. My concentrated HCl here at 12 molar, remember I needed 125 milliliters, that's what I calculated. So I'm measuring that out to 125 milliliters, as close as I need to. And then I pour that into the water that's already in my 500 milliliter flask. The next step is I'm going to dilute to the mark on the flask, and then just before I get to the top, I'm going to cover it and I'm going to invert several times to make sure that it's all mixed. And when you're doing this, you can actually see the solutions mixing because they interact with light in different ways depending on their concentration. When you can no longer see this sort of swirling light effect, you know that it's all mixed, and then you can top it all the way off to the mark. So visually that would look like this. Add water till near the top, put a lid on it, flip it over a few times, and then you take the lid off and put the very few last drops in the top.